Xavier College once again. I think I was there almost 1 year back for a conference. Today I am really pleased to be here in this wonderful college again. Actually, you are really amazing students, and I am fortunate enough to guide one of St. Xavier student for his PhD. He did extremely well under my guidance for his PhD. When I came last time, I mostly talked about his work. Since I already talked about the ruthenium chemistry today, I thought I should talk some other chemistry. That's why I selected the cobalt catalysis. If you look at the science of history, particularly catalysis, there were many industrial catalysis developed using cobalt as a catalyst. For example, the acetic acid process and even hyperformylation process. They were originally developed using cobalt catalyst. But over the time, in search for better stability and as well as selectivity, almost not only these two processes, almost all the industrial processes were developed using precious transition metal catalyst. But now there is a renowned interest in the base metal again due to their increased cost as well as enhanced awareness among the people, okay, including scientists. So once again we are revisiting the base metals, particularly cobalt is very interesting base metal because it gives very new reactivity every time. And one other topic that we might have studied is metal ligand cooperation. What is metal ligand cooperation? In general, in catalysis, particularly the catalysis by homogeneous transition metal complexes that happens under like solution phase condition, the ligands do not participate in the reaction. Almost all the bond formation and bond breaking reactions occur at metal center. The ligand simply acts as a mute spectator, holding the integrity of the metal complex, so that the metal can carry out all the transformations. On contrary, there are classes of metal complexes in which not only metal, also ligand play important role in both bond formation and bond breaking reactions. Such reactions are called metal ligand cooperation. So today I am going to talk about such reactions in which not only metal, also ligand participate in the reaction using cobalt catalyst. Okay. White base metal. Some of the terrestrial abundance of the base metal are in the 10 to the power 4 orders of magnitude that of the precious metals. So their increased use will lead to reduced environmental footprint. Not only that, they are also much cheaper compared to the precious metals. In addition to that, they are relatively non-toxic. This though almost completely green except the copper. So their use can result in reduced toxicity to the environment. Further, although they have much advantages compared to the precious transition metals, their use in the catalysis comes with their own challenge, because the 3D transition metals have reduced orbital overlapping with the bonding partners compared to their 4D and 5D counterparts. This reduced orbital overlap deficit has tremendous influence in the electronic structure of their catalyst, because this reduced orbital overlap leads to the ionic character in bonding with the metal and the ligand. As a result, they have a small d orbital splitting, which leads to the stabilization of high-spin electronic complexes. As a result, they tend to favor one electron redox process, whereas the noble metals, they always favor two electron redox process. Okay, so there is a fundamental difference between the 3D metals and the Nobel Transition Medals. In addition to that, they also have different redox potentials. But if you look at the redox process essential for life that are facilitated by metalloenzymes, all of them are exclusively featuring the base metals. So how nature manages the 2-electron redox process using the base metals, that favors only one electron redox process. So if we look at the nature way of doing catalysis and understand them properly, then we can mimic them in the chemical catalysis process. Actually, nature does this using the help of the ligand framework, which is amino acid in the case of metalloenzyme catalysis. For example, the iron hydrogenase enzyme and even the photochemical synthesis or this oxygen and CO2 reduction by metalloporphyrin, all this involves 2-electron redox process involving the help of metal ligand cooperation framework. So using this such metal ligand cooperation, there are many pincer complexes developed which facilitate the electron redox process just by using cobalt. What is pincer complexes? The tridentate ligand. You see, Y and X, they are the donor atoms. So this tridentate ligand, which enforce meridional geometry. This geometry, when complexed with metal precursors, are called pincer complexes. This is not a very definite description, but they are called pincer type complexes. This tridentate coordination brings much stability to the complex, which can also be fine-tuned. As the ligand framework coordinates in a tridentate fashion, they take out most of the coordination site, free coordination site on the metal. So as a result, they impart much selectivity to the chemical reactions. Not only that, this pincer framework imparts coplanarity around the metal center. As a result, the stability of the complexes increases. You know, like many metal complexes of pincer type are stable even at 200 degrees Celsius. You know, like this is one of the major drawback of many homogeneous catalysts, which means start to decompose at the temperature above 120 or 150 degrees Celsius. So they will lose their integrity. Whereas the pincer complexes, they will stay very stable even at high temperature. As a result, the thermodynamically high barrier chemical reactions can be carried out using such pincer catalyst. Okay. So there are many cobalt catalysts developed before us by this renowned scientist. We have introduced one cobalt pincer catalyst using a simple ligand framework NNN. This is how the pincer ligands are classified using the donor atoms nitrogen, and we attempted the dehydrogenate the oxidation of silanes using water. We actually wanted to oxidize the silane to silanol and liberate hydrogen. But what actually happened was it resulted in complete dehydrogenation, leading to the siloxane synthesis. So the only byproduct in the reaction is 2 equivalent of molecular hydrogen with just 2 more % of catalyst, and just heating at 60 degrees Celsius in 2 hours, we get almost quantitative of siloxanes with excellent compatibility to the steric hindrance. You know, like you can see that the siloxanes are highly sterically crowded, still the reaction works very nicely. Not only that, when we used dihydrogen in the reaction, it led to the formation of tetrasiloxanes macrocycles with liberation of molecular hydrogen. Very interestingly, when we use the primary silane, phenyl silane with 3 hydrogens, the reaction progressed in 3-dimensional space, leading to the formation of the siloxane cage. Actually, this siloxane cage is commercially available. This is synthesis using multi-step process. Whereas using the silane and just water, we can get this siloxane in just one step And the only byproduct is threefold release of molecular hydrogen. 36 equivalent of molecular hydrogen. You know, like this is a very beautiful reaction because the only byproduct is molecular hydrogen, which is not that harmful, and it can also be very valuable energy source. Next slide. Further, we have coupled selena with dihydrosilane as well as trihydrosilane, which led to the formation of higher order siloxanes having silane hydrate in the product. Okay, these are very valuable siloxanes because they are used in many material applications. Next slide. Further, you all might have learned the alcohol oxidation in your chemistry textbook, organic chemistry. You might have learned Jones oxidation reactions. For example, you need Jones reaction is a beautiful reaction, but you need 6 equivalent of bromide salt to oxidize 1 equivalent of alcohol to corresponding carboxylic acid. Whereas here, you see just 2% of this cobalt pixel catalyst and stoichiometric amount of base. Heating at 140 degrees Celsius for 6 hours followed by acidic workup, we will have the corresponding benzoic acid in very good yields, and the byproduct is only molecular hydrogen. Next slide. Further, not only benzoic alcohol, we can oxidize any aliphatic primary alcohols, including the ethanol, and even the sterically hindered systems like ring strained with the 4-member ring, cyclobutane, and strained system, very sensitive cinnamide alcohol, all of them oxidize to the corresponding carboxylic acid. Interestingly, even the diols are oxidized to the corresponding dicarboxylic acids. Next slide. The mechanistic studies showed that the reactions are homogeneous. Actually, mercury is a poison to the homogeneous catalyst. Heterogeneous catalyst. If the reaction involves the heterogeneous catalyst, the mercury amalgam will populate that heterogeneous catalyst and prevent the reaction. Whereas when we use mercury in our reaction, the reaction works nicely with 82% yield, telling that our reaction proceeds via homogeneous catalytic pathway. So that means the catalyst remains intact. Further, we could detect the hydrogen using gas chromatography, and we also quantified the amount of hydrogen that releases from the reaction using gas burette reaction. Further, when we use only aldehyde and in reaction with base alone, we have obtained this is a conditional reaction. We have obtained carboxylic acid and alcohol. However, when we reacted aldehyde and alcohol in the presence of catalyst, only 9% of corresponding ester was observed. This indicates that the ester may not be the true intermediate in our reaction. So, further, when we reacted only aldehyde, no ester formation was observed. So, this indicates that the reaction goes via the aldehyde formation, not preferably via ester formation. So, but without base, when we reacted only with water, no reaction occurred. So base is essential to the reaction. So based on this, we proposed the mechanism that the catalyst react with the base to equivalent, leading to the dehydrohalogenation reactions that provides cobalt T complex, cobalt 2. Sorry. That is OH bond activation of alcohol, leading to this alkoxy complex, where one of this alcohol OH proton is accepted by one of the amine arm. This is where the ligand participates in the catalysis. Because after activation, the proton goes to the nitrogen donor atom. This donor atom acts as a proton acceptor. So this alkoxy ligand is eliminated as an aldehyde via beta hydrate elimination. That provides the aldehyde intermediate, to which the KOH undergoes attack, leading to the potassium heavy acetaldehyde intermediate that generates the cobalt hydrate. So this cobalt potassium hemiacetylate. This is a very reactive intermediate which is again oxidized by the catalyst intermediate 1, leading to this alkoxy type of intermediate. From that, the another equivalent of cobalt hydrate generates, and this cobalt hydrate and the proton from the nitrogen can come back and generate the non-classical hydrogen coordinated to metal, which can liberate the molecular hydrogen. So through this pathway, one equivalent of hydrogen, through this pathway, another equivalent of hydrogen. So total two equivalent of hydrogens are liberated as a byproduct. Further, we could selectively reduce esters to aldehyde and alcohol using silane as a reductant. When we use only 1.5 equivalent of silane, the reaction stops at silane acetate intermediate. Further workup provided exclusively the aldehyde as the product. When we use the 3 equivalent of silane in the same reaction, next here. Conditions are same. Both reactions takes place at 50 degrees Celsius. The previous reaction takes longer time, but when we use the 3 equivalent of silane at say 50 degrees Celsius, in 20 minutes the reaction is complete. The complete reduction takes place. The complete reduction of the ester carbonyl functionality, leading to the exclusive formation of primary alcohol. Even the dicarboxylic ester can be selectively reduced to diol. Most of the time when you reduce dicarboxylic acid, intramolecular cyclization will take place. But whereas here, it selectively reduces both ester independently and gives diol as the final product. Immediate studied British reaction. This reaction occurs stoichiometric amount of lithium metal. You know how difficult to handle lithium metal. If you open the atmosphere, sometimes if your atmosphere is wet enough, it can even catch fire. Very difficult to handle that. You need a cryogenic conditions to perform the British reaction. Whereas here, we use the cobalt catalyst and transform the ether to secondary alcohol, that is classical 1,2 British rearrangement. Using silane as a hydrogen source, almost we could transform any ether to secondary alcohol. There is only one caveat. At least one of the alkyl groups should be benzylic in nature. Because the reaction goes via the radical pathway, that benzyl radical should form in the first place. If both sets are alkyl aliphatic chain, then the reaction will not take place. Otherwise, having one set benzylic substitution, any ether can be transformed to the corresponding secondary alcohol. Even sensitive functional group like bromide or sterically chloride functional group are work very nicely. Yes. The mechanical studies clearly indicated that the reaction goes via homogeneous pathway. Mercury did not prevent the reaction. When we use the radical scavengers like tempo, the reaction completely prevented. So this clearly tells that the reaction goes via the radical pathway. Further, when we use this sodium toluene sulfonate, we could trap this benzylic radical and we could isolate this product with 30% yield. And in this aliphatic ether with the alkyl chain, we could also trap this alkyl chain. So this indicates that from both sides the radical intermediates are forming in the reaction. So we could trap both benzylic as well as aliphatic radicals. Further, before workup, when we intervened the reaction, we could isolate the silane ether intermediate in almost quantitative yield. This clearly tells that the reaction indeed progressed via this silane ether intermediate, which upon hydrolysis gives the secondary alcohol product. When we introduced the secondary alkyl group as part of the ether, we got the distilleric secondary alcohol in reduced yield. Further, when we made one of the ether alkyl substitution as a tertiary alkyl unit, the reaction completely prevented. So these two reactions clearly tells that the reactions are highly sensitive to static hindrance. Okay. So primarily you need primary alkyl units for the better reaction. Next. So based on this observation, we propose the mechanism that after double dehydrohalogenation reactions, the ether coordinated catalyst intermediate is forming, which upon reaction with base and silane generates this benzylic radical in the beginning, and the subsequent the alkyl silane ether coordinated radical intermediate is forming, which dissociates this radical intermediate, which undergo radical combination with this benzylic radical, generating the silane ether intermediate, which is isolated and characterized, and further hydrolysis gives the secondary alcohol as the selective product. Further, we have done series of deoxygenation reactions using this catalyst. There are several catalysts for the deoxygenation of aldehydes, alcohols, and other functional groups. But every reaction factors different catalysts. Whereas using this one catalyst, we could selectively deoxygenate n number of aldehydes to the corresponding alkanes. You can see that highly functionalized aldehydes like carbazole aldehyde can be deoxygenated, and even the cinnamyl aldehyde can be deoxygenated to the corresponding alkanes, or even the heteroarenes are tolerated. Further, deoxygenation of ketone also works with the same catalyst. 3 more % of catalyst, 20 more % of base, heating at 100 degrees Celsius in 24 hours. We got very good yield of the corresponding alkanes. You see this is actually a 1,2 type ketone. Even both carbonyl groups adjacent to each other are completely deoxygenated to get the corresponding 1,2 diphenyl ethane. This is 3-indole acetone, completely deoxygenated. Only here we started the reaction with this 9-acetyl anthracene. But in this case, instead of the anticipated deoxygenation, we got deacetylation. This is because this group is orthogonally coordinated with this extended aryl group that has electronic influence. As a result, this carbon-carbon bond is weak, which got cleaved during the reaction. Next is the deoxygenation of alcohol. I give only the limited number of examples. Almost like any alcohol that we have can be deoxygenated using this reaction. Benzylic alcohol, substituted benzylic alcohol, even this androgen methanol can be deoxygenated. Perennial alcohol, ferrozine methanol. Not only this benzylic alcohol, any aliphatic alcohol. This is actually aliphatic diol. Both hydroxyl groups are deoxygenated, and the corresponding longer chain alkanes are obtained with very good yields. These two are secondary alcohols. Reaction also applicable to primary alcohol, secondary alcohol, and also tertiary alcohol. See, this is the tertiary alcohol. Completely deoxygenated, and we can get back the alkanes with very good yields. Next slide. The reaction also works to the deoxygenation of ether. If you take symmetrical ether, oxygen is removed, and you get 2 equivalent of corresponding alkane as the exclusive product. If you take unsymmetrical ether, you get mixture of alkanes. You have 2 different units, both will form together. Only thing, the isolation of this resulting alkanes will be very difficult. But you can, as a mixer, you can isolate the products. Next. So we also deoxygenated the oxygen containing compounds derived from biomass compounds. This is very relevant to the synthesis of biorenewable chemicals. For example, this perfurol and this hydroxymethyl perfurol and this kind of benzylic alcohols are very much obtained from the biomass. So all of them are deoxygenated. Only this perfurol, they are very sensitive functionality. The yields were low, but this one we recorded very good yield. Next slide. The reaction mechanism of this process was really challenging, but we took extraordinary effort where we have almost got this mono deprotonated complex which formed in particular in 2 hours. Beyond that, this complex undergo disproportionation leading to this cobalt dibromide, which only we could get the crystal structure. So we took the DFT help to understand the reaction mechanism, which clearly indicated that this cobalt complex exists in different spin surfaces. Like both cobalt triplet and singlet states are involved during the reaction. Okay. This we could also observe experimentally because when we took the proton number of the reaction mixture, we observed more than one hydrate in the N number. Okay, so this indicates that there is a coherence between the DFT calculation and the experimental observation. Okay. That's it. There were many other stoichiometric experiments. When we used aldehate, we could isolate the silyl ether intermediate, and further, after isolation, this reaction gave alkane. So this is silyl ether intermediate is confirmed. And same is true with ether. We could get the silyl ether intermediate. With ketone, we got directly the alkane. And when we used mercury, the reaction did not stop. So this indicates again the reaction is homogeneous. But when we used tempo radical scavenger, no reaction. So the reaction involves radical positive. And further, the radicals are trapped using this sodium protein sulfonate. When we use this deuterated alcohol and silane reductant, the deuterium on the alcohol remained intact, and we could exclusively introduce one proton. So this clearly tells that the deoxygenation is not undergoing via dehydrogenation. It removes only selectively the oxygen and installs the proton, because you can see the nuclear percentage both in benzylic alcohol and in the alkane, 95% it remains the same. Next. Further, when we use the isolated intermediate that we got in 2 hours with no base, the reaction works beautifully. And with the base, we got even better yield. So this clearly tells that the role of base is to introduce the active catalyst, and also it plays essential role in catalysis to enhance the yield of the product. Further, the same observation was observed with the ether, and as you can see that this intermediate further reacts with the silane, and we have observed actually 2 hydrate signal in N. This also matches well with the DFT calculation that it's showing both cobalt triplet and similar surfaces are involved in the reaction. That's right. Actually, this is the extensive DFT calculation. For the benefit of time, I will not go into the detail. But you can see that the hydrosilylation reactions of aldehate functionality is very present. It involves only 12, around 8 kcal per mole, which is a very present reaction. And as you can see that the reaction proceeds via singlet intermediate as well as the triplet intermediate. They exchange at a point called the minimum energy crossing point, MCP. Okay. At this minimum energy crossing point, they switch the spin states from singlet to triplet or triplet to singlet. So this is the reaction that reaction was calculated with no additional cooperation from the ligand framework, which required around 21 kcal per mole without ligand participation in the reaction. But when we calculated the reaction with ligand participation, you can see that the maximum value is only 11.8 kcal per mole with ligand participating in the reaction. So the reaction preferentially works via the metal ligand cooperation pathway. Next. So this is a reaction pathway for hydrosilylation of ether, which requires relatively high energy because the ether is a very robust and strong functionality. Next. So based on this experimental observation as well as the DFT calculations, we propose the mechanism that base does double deep hydrohalogenation, leading to this silane hydrate intermediate, which is this intermediate is observed in the mass spectral analysis. Further, the cobalt hydrate undergoes hydrosilylation reaction to the carbonic compound as alternate or ketone, leading to this hydrate addition to this carbonic functionality, generating this alkoxy intermediate, which this intermediate, alkoxy silane intermediate, also observed in mass spectral analysis. Further, the the bond formation takes place between this alkoxy ligand and silyl ligand, leading to the silyl ether coordinated intermediate, and this intermediate is also observed in the hospital analysis. And further elimination generates the silyl ether intermediate, which is further undergoes the deoxygenation reaction to deliver the alkene product, and further coordinates with the silyl generate the catalytically active intermediate for deoxygenation of aldehyde and ketones. For alcohol and ether, the reaction mechanism is slightly different. For alcohol, the silyl ether intermediate does OH point activation involving this metal ligand cooperation, where the proton is accepted with this amine arm, and that generates this silyl ether intermediate, which is eliminated, and this cobalt hydrogen non-classical hydrogen complex generates and liberates the molecular hydrogen that comes back to the active catalyst intermediate, the triplet state intermediate after reaction with the silyl. For ether, the ether coordinates that generates this cleavage of this alkane that liberates out. Further, the silyl ether intermediate which liberates and comes back and reacts with the further catalyst with silyl generates the second equivalent of alkane from the ether. The byproduct are siloxane ether. Very recently, we could also carry out the complete deoxygenation of ester to alkanes. This is very important because there are many esters that are naturally available. So all of them can be deoxygenated to synthesize the corresponding alkanes. So we can get the alkane from the bioradiographic compounds. As you can see that many benzylic esters, even the cinnamic ester can be deoxygenated that work with migration of the double bond. Next. All these esters, actually these are alkanes, prepared from the esters which were prepared from commercially naturally available carboxylic acid. All these carboxylic acids behind this ester used in these reactions are naturally available. So we could produce it from biomass. So we made ester out of those chemicals, then deoxygenated them and prepared the corresponding alkanes which were obtained in decent vehicles. Like salicylic acid, nicoquine, vanillic acid, nicodinic acid. These are commonly available carboxylic acid which were deoxygenated to the corresponding alkanes. The mechanistic studies once again give similar observation that reaction is radical pathway and the radical is trapped. Silyl ether intermediate involved. This is the silyl hemiacetal, and this intermediate also trapped, and even here the aliphatic silyl ether was trapped, and then this alkane is absorbed in very good yield. Next. Based on this, the mechanism is proposed. It's similar to the carbonyl hydrosilylation mechanism, where the cobalt hydride is transferred to the ester carbonyl, generating this hemiacetal intermediate, and this alkoxy silyl coupling takes place in the next step, which eliminates to undergo further complete deoxygenation, and for the reaction silyl will generate the catalytically active intermediate, and these intermediates were observed in the mass spectral analysis. So with this, I summarize the cobalt catalysis using very simple and our cobalt catalyst prepared from very simple NMN ligand framework in simple synthetic steps. We could carry out the oxidation of silane to siloxanes and cross-couple silanol with different silanes to obtain higher order siloxanes, and oxidize selectively primary alcohol to carboxylic acid, in which the only byproduct is molecular hydrogen, and selectively reduce esters to aldehyde or alcohol, in which the selectivity is controlled by the stoichiometry of the amount of silane used in the reaction. Further, we have invented the first catalytic 1-to-50 rearrangement in which we have transformed ether to secondary alcohols for the first time and reduced ester to alkanes, aldehyde indicator to alkanes, and alcohols to alkane, in which again the reaction proceeded with liberation of molecular hydrogen, and ether to alkane. So most of this work are carried out by my student Sandeep Patnaik. How much time we have? How much time we have? I can finish that 15 minutes. 10 minutes? Okay. So, recently we have also started working with cobalt catalyst. Next slide. In which we have used the same copper catalyst, the same NNR ligand, and prepared a copper catalyst, in which we have obtained a cationic copper complex, and using this copper complex, we have carried out a very interesting reaction to selectively hydrogenate the quinolines. Like the quinolines, it's a very interesting biological molecule, and also the product formation involves the thermodynamics. Due to thermodynamics of the reaction, the complete hydrogenation of the sector is very favorable. But selective hydrogenation of this only one nitrogen carbon double bond is very challenging because the products are thermodynamically more less stable compared to the starting material as well as the complete hydrogenated product. So the reaction is thermodynamically uphill, and designing such catalyst and catalytic reactions is really challenge for the catalysis. Whereas here the copper, which is a very soft in nature, could selectively reduce only the carbon nitrogen double bond, and we could get this such partially hydrogenated product. Actually, these products are very unstable. We could observe those products only in NMR. If we try to isolate, they tend to re-aromatase again. So, even for isolation, such products are it's very challenging. But we develop a catalyst that can selectively catalyze such hydrogenation process. Next slide. As a result, we face the isolation problem. Instead of trying to isolate as a partially hydrogenated product, we isolated such amines, and the corresponding acyl 1-to-hydrogenated quinolines are obtained very good yield. And you can see that having excellent functional group tolerance, the products are isolated. But when we have different aromaticity, the corresponding amines were isolated in very good yield. Yeah, the mechanics studies showed that when we use the labeled ammonia body, which is used as a reductant, selectively 99% of deuterium is incorporated in the quinoline 2 position. This clearly tells that the hydrogen to the quinoline 2 position comes from the boron unit, and to the NH comes from the ammonia unit. Further, when we did the stoichiometric reaction between the catalyst and the lithium base, we could exclusively obtain this intermediate 2, which is obtained from catalyst disproportionation reaction that occurred, in which the intermediate has a very it's a new type of formation where the copper 2 metals are involved in the catalyst intermediate, and we have the X-ray section of this intermediate. This is the 2 intermediate involved in the catalyst. So using the isolated intermediate 2, we could carry out a similar reaction, and when we carried out the reaction in a higher scale, we also observed this intermediate in the reaction. So in the following the kinetics, we have observed the same catalysis with the catalyst 1 as well as intermediate 2 in 1 hour. So this clearly tells that intermediate 2 is the real catalyst involved in the reaction. So this is the proposed reaction mechanism where this intermediate 2 formation, which is confirmed further reacts with ammonia borate and coordinates the boron unit to the copper and the amine unit to the nitrogen, and the boron transfers exclusively the hydrogen to copper and the ammonia unit transfer hydrogen to the amine arm, leading to the dihydro amine unit, and this copper hydrate and this amine proton are concomitantly transferred to the nitrogen and carbon selectively so that it can deliver the 1,2-dihydrogenated quinones. So we also have manganese catalysis, but I think in the interest of time, I will not go into further detail. I will just show one or two results. Next. Using this manganese mixer catalyst, we have selectively introduced cross-coupled various organic functionality with alcohol, in which alcohols are used as a direct alkylation or alkylation partner, in which in all the reactions only water and molecular hydrogen are the only byproducts. Next slide. Very recently, using this manganese bromide salt as a catalyst, we have antimorphic addition of this diallyl phosphine oxide to the allylic alcohol, where we have got the hydroxyphosphate synthesis directly from the allylic alcohol for the first time. Starting from alcohol, we end up with the alcohol. This is the video of this reaction. Next. Almost any secondary allylic alcohol can be employed in the reaction, and the corresponding products were isolated very good here. And the products can also be modified to other functionalities, which is also demonstrated in the paper. So this is the proposed mechanism that involves one electron redox process. This is no pincer. We take the manganese salt as a precursor, as a catalyst, and as a result, we using one electron redox process, we have obtained this hydroxyphosphate synthesis. So this is a routine chemistry that I already spoke to during the last year, and I think my student also recently gave talk on this topic recently in this college. So I am not going into further details. Just go to the next. Yeah, this is another area that we work. By using this protein sandwich complex, we selectively de-aromatic the heteroaromatic compounds in either in 1,4 fashion or in 1,2 fashion using the hydroxylation or hydroboration reactions. So this I thank all my co-workers for the fantastic contribution as well as hard work, which gave all the results. You know, like they do all the work, I take all the credit. So I thank all my PhD students and also all my MSc students. They are wonderful students. Most of the students are doing PhD abroad. Some of them have already become faculty in IIT. You know, like Akash Kejal is faculty in IIT Kharagpur, IIT Roorkee, and others also faculty in other NIT and other places. And I also thank my collaborators, Professor Leitner, Dr. Alexis Pogan from the Max Planck Institute, and Dr. C.H. Suresh from Mr. Trivandrum, Rosita from IIT Palakkad, and Professor James from IISc, all of them, and also Professor Ludraj, who is my own colleague. All of them contribute extensively for the DFT calculations. So I thank all of them who really help us to solve the important problem. I also thank the funding agency for the generous funding. With this, I thank you all. If you have any questions, please feel free to ask. Yeah, in case you are interested, you can ask me after the talk over. I will be happy to answer any queries that you have. And also, we are keenly looking for the PhD students. So first you qualify, first you complete your MSc, qualify CSR, JRF, then you apply to us, we will be happy to hear you. If no questions, I am done. Any questions you can ask me freely, no problem. If you don't have your, please say I don't know. You know what? You know what it is? This is what I explain.
Sir.
Yes, please. Yeah.
We saw deoxygenation of ketone. We have studied Prof. Krishna.
Yeah.
What's the difference between cobalt tensor complexes as well as the reagent?
Okay, very good question. Actually, Clemenson reduction is the heterogeneous process. Okay. And the catalyst is not heterogeneous. This is a homogeneous catalyst. Got it?
Sir, if we use the tempo, it tells that the reaction mechanism is free radical based. What is the character of tempo, sir? What is it actually?
Tempo is a free radical. Challenges are getting same reactivity as that of precious metals. The precious metals, they have very good properties. For example, sometimes can even carry out reaction to one mode catalyst, even five mode catalyst. Whereas in terms of reactivity, these metals still cannot match. But for that, continuous catalyst structure can overcome. Okay, I'm done. Thank you. Faculty members, non-teaching staff and students, good afternoon to everyone. In particular, I would like to thank Dr. Stanley Joseph and Dr. Kumar for the invitation to deliver Gnanaraj Endowment lecture. So today I am going to talk about our group research on the evaluation of various pronucleophiles for the construction of various carbon and carbon heteroatom bonds. So, for the sake of convenience, I have divided my talk in two parts. The first part involves exploration of carbon-based pronucleophiles for the construction of various carbon-carbon bonds. In the second part, I will be discussing about exploration of sulfur-based pronucleophiles for the construction of various carbon heteroatom bonds. In the first part, I am going to talk about exploration of carbon-based pronucleophiles for the construction of various carbon-carbon bonds. So, before going to the details, my talk totally involves on the use of is the one which is a negatively charged species, right? Or it can be a heteroatom with a lone pair. Then pronucleophile is the one. It can be an organic compound with acidic proton, but pronucleophile itself cannot be a nucleophile. However, it can be converted into corresponding active nucleophile in the presence of either base or acid. Here, since this carbonyl compound, which is considered as a pronucleophile, has acidic proton at the alpha carbon, so when you treat this carbonyl compound with the base, it obstructs the acidic proton, it forms the corresponding carbanion, which is called as an active nucleophile. So our group largely involves the activation of pronucleophiles having high pK value. We all know that high pK value means less acidic. So we would like to use either Bronsted base or the cooperative catalyst consists of Lewis acid and a mild base. So we would like to activate the less acidic pronucleophile as shown here. Then you generate the active nucleophile. Then the in situ generated active nucleophile can be trapped with the various electrophiles to form this desired product. So our group was interested in the activation of less acidic pronucleophile. Here we chose alkyl azarin as the pronucleophile because it has a less acidic proton at the alkyl side chain and its pK value is approximately 30. It is purely acidic. So So we would like to use the metal Lewis acid or mild base combination or a strong Bronsted base. When you treat either metal Lewis acid or a counterion of the strong Bronsted base can coordinate with the nitrogen atom of the pyridine. This coordination takes away the electron density from the nitrogen. Eventually, it makes this alpha proton highly acidic than the parent alkyl pyridine. Next. So when you treat this species subsequently with the counterion of the base, it obstructs this activated proton, it forms a corresponding carbanion. This carbanion will be stabilized through the carbon-nitrogen bond present on the pyridine and it will form the corresponding next. The metal enamide nucleophile. We would like to use this metal enamide pronucleophile for the 1,6 conjugate addition reaction with the paraquinone methyl. Next. The paraquinone methyls are the derivatives of parabenzoquinone. In parabenzoquinone, one of the carbonyl group is replaced with a methyl group. This paraquinone methyl is inherently electrophilic at the delta position because of the presence of this pseudoionic structure. Right? The gaining the aromaticity is the driving force for the electrophilicity at the delta carbon. However, paraquinone methyl itself is not a stable compound. One has to attach a bulky group to prevent the polymerization. Next. In generally, bulky substituents are added at the 2 and 6 position of the paraquinone methyl. This also gives 2 addition as well as 1,4 addition are shown here. It only reaches selectively facilitate the 1,6 conjugate addition as shown here, and it forms the corresponding 1,6 adduct as a product. With this plot in mind, we subjected this alkyl azarin for the 1,6 conjugate addition reaction with the paraquinone methyl, and we have screened various reaction parameters, and we found that the use of 2 equivalents of sodium HMDS, so the structure of the sodium HMDS base is given here. It is almost similar to LDA. The use of 2 equivalents of sodium HMDS as the base led to the formation of the corresponding 1,6 adduct in moderate to excellent yield. Next, after developing the method, we would like to probe whether this method is general for all the substrate. So, the alkyl azarin is similar substrate, 2-methylquinoline, 2,6-lucidine as well as 2,4-trimethyl pyridine also underwent facile 1,6 conjugate addition reaction and furnish the desired product in moderate to excellent yield. It is important to note that when you have methyl group at the 2 and 4th position, the reaction exclusively occurred at the 2 position of the pyridine. Subsequently, we have subjected for 4-methylquinoline as well as 4-methylpyridine also. It works very well and furnishes the desired product in moderate yield. Next. Apart from the single methylpyridine, even pyrazine and quinoxoline, even 1-methylquinoline, even benzothiazole also works very well. Apart from screening various alkyl azarin, we wanted to screen various paraquinone methyl having different substituents such as naphthyl and paraquinone methyl having electron donating group and even halo substituent. None of them works very well and furnishes the desired product in moderate to excellent yield. Next. So far we have used pre-synthesized paraquinone methyl. We wanted to make this paraquinone methyl in one part. One part means you take the aldehyde as well as the corresponding phenol derivative, you make them one part, don't isolate, and you subject this for 1,6 conjugate addition with azarin, then we were able to synthesize the respective 1,6 conjugate adduct in 56% over 2 steps. Next. So since I have told the tertiary butyl group provides the stability to the paraquinone methyl, at the end of this reaction, we wanted to cleave the tertiary butyl group. We subjected this product for detertiary butylation reaction in the presence of Lewis acid, and we were able to get the corresponding detertiary butylated product in good yield. Next, whatever the methodology we developed, we try to understand the mechanism of the reaction. In order to identify the precise reaction mechanism, we have performed the control experiment, because in the introduction I have mentioned that the counter ion will coordinate with the nitrogen atom of the pyridine. So if you want to know whether counter ion is actually playing a role in this reaction,
we devised a few controlled experiment in the presence of crown ethers. Right? Yeah, we all know that the crown ethers are known to bind with the alkali metal ion. If you use 18C crown ether, it can bind with the potassium and sodium. If you use 15C crown ether, it can bind with the sodium. So which means if the crown ether is binding with the metal ion is not available for the activation of the nucleophile. So with the thought in mind, we devised here three reaction. We used KHMDS, soda HMDS and in the presence of crown ether, we can able to only observe trace amount of product formation or less yield, which indicates that the counter ion plays an important role in this reaction. Based on this information, we proposed a plausible reaction mechanism. When you use a sodium HMDS as a base, the counter ion coordinates with the nitrogen of the pyridine, which enhances the acidity of the alpha proton. Then the counter ion of the strong bronzed base upsets the acidified proton and it forms a metal enamide. Now the metal enamide again binds with the paragonine with a double bond. Then flow of electrons start from here and it attacks the delta portion of the paragonine method. Then the electron moves towards the carbonyl group and eventually it forms the corresponding phenoxide ion intermediate. This phenoxide intermediate upon protonation gives the corresponding 1,6 adduct. Next. So far I have discussed about the 1,6 conjugate addition of alkyl azarin. Next we were wondering, if you have alkyl azarin, whether is it possible to subject this alkyl azarin pronucleophile for the 1,6 conjugate addition reaction. Next. When you subject this one, the proportionally CH bond can be abstracted and it will form the corresponding proportional anion. And the problem associated with the proportional anion is it will be the isomerization with the aluminum anion. And it is very difficult to control the isomerization of proportional anion to aluminum anion. So we were thinking that is it possible to subject this alkyl azarin for regioselective elimination as well as regioselective proportionation by tuning the reaction condition appropriately. Next. So with this thought in mind, we went on to synthesize the alkyl azarin from the pyridine carboxyaldehyde over two steps. The first step involves Wittig type reaction to furnish the corresponding dibromo-olefin. Then second step involves the butyl lithium abstract the proton from the dibromo-olefin. It forms a terminal alkene. Then terminal alkene reacts with another equivalent of butyl lithium, and further that lithium acetylide undergoes nucleophilic displacement reaction with the methyl iodide. It forms the corresponding alkyl azarin. So after successfully synthesizing this alkyl azarin, we went on to probe our thought whether we can subject this for regioselective elimination as well as regioselective proportionation. So with this thought in mind, we screened the various conditions and we found that the use of 1.5 equivalent of potassium tertiary oxide as the base exclusively led to the formation of the corresponding allylated product. Whereas the use of 2 equivalents of sodium HMDS as a base led to the formation of corresponding proportionated product. Next, we have evaluated the scope of this reaction by varying the substituent on the paragonine method, different electron donating substituents like methyl, amino, even halo substituents such as chloro, bromo, electron withdrawing groups such as cyano, HURI, all of them tolerate under the reaction condition. It is important to note that nowadays deuterated organic molecules receive considerable attention in drug discovery. Even deuterated internal alkyne also underwent facile 1,6 conjugate addition and formed the respective product in 98% yield. And interestingly, when you have alkynyl group at the 3 position of the pyridine, the reaction did not work, which indicates that the carbon ion is not stabilized by the nitrogen when it is in 3 position. Subsequently, we have probed the scope of the even alkyl azarin also. Alkyl azarin having quinoline, methoxypyridine, methyl and pyrazine and benzothioazole, benzimidazole, benzoxazole also underwent facile reaction and furnished the desired product in moderate to excellent yield. Next we were investigating the scope of the propagylation reaction also, and we were able to synthesize the desired propagulated product in good to excellent yield. Next. So in order to show the synthetic modification of the product what we synthesize, first we have subjected this molecule for deterioration reaction. Subsequently, this hydroxyl group was converted into methyl ether by treating with the sodium hydride. Subsequently, trapping the corresponding phenoxide ion with the methyl iodide, we were able to synthesize the corresponding methyl ether. Next, we have subjected this allylated product for the copper mediated borylation reaction, and we were able to synthesize the corresponding borylated tetracyclic treated olefin. Next, and also we have subjected this allyl product for the copper mediated silicylation reaction, and we were able to obtain this silylated product in 57%. Then we have subjected this intramolecular cyclization with the pyridyl nitrogen. We were able to synthesize the corresponding molecule in indolysine molecule in 99%. Next, even propagylated product also we have protected this hydroxyl group. Subsequently, we have subjected for palladium mediated reduction. The alkyl unit was reduced to the corresponding saturated alkane. Next, even this reaction works in gram scale. This tells about the scalability of this reaction. Next. So, in order to understand the reaction progress, we propose a plausible reaction mechanism. Here, the counter ion of the potassium trisulfite oxide coordinates with the pyridine nitrogen as well as the alkyl unit. This coordination enhances the acidity of the propargylic C bond. Then the activated bond is obstructed by the trisulfite oxide ion, and it can form the corresponding propargyl species or allyl species. Right? Both propargyl species and allyl species are called as amidal nucleophile. We all know that what is amidal nucleophile means. The nucleophile having two nucleophilic center. Here, the reaction of propargyl species with the electrophile can take place either at the alpha position or at the gamma position. Whereas in the case of allyl species also, the reaction with the electrophile can take place either at the alpha position or at the gamma position. So, in order to understand which species is the active species in the formation of allyl product, we took the help of DFT study. Suppose if the potassium propargyl species is an active species, then if it has to install allyl functionality, it has to go for a gamma attack. So here, the bond between potassium and carbon breaks and it comes here. Then the transfer of electron from gamma group to delta position of the paragonal method takes place. Then the flow of electron towards the carbonyl group gives the corresponding alkoxide. Further protonation can lead to the formation of corresponding allylated product. So we have taken the DFT help to calculate the energy barriers required for this reaction. It was almost calculated as 13.3 kilocalories per mole. Subsequently, if this is the active species in the reaction medium, then it can undergo alpha attack as shown here. It can give the corresponding allylated product. Then we have calculated the energy barrier for the alpha attack of the potassium allyl species. It was 7.5 kilocalories per mole. So which indicates that when you compare these two values, this is the energetically favorable process, which means the alpha attack of the potassium allyl species with the paragonal method can lead to the formation of corresponding allylated product. Next. In the case of propargylation reaction, in the presence of sodium HMDS, even sodium propargyl species can undergo a alpha attack to form the corresponding propargylated product. On the other hand, next, the gamma attack of the sodium allyl species also can lead to the formation of corresponding propargylated product. We have calculated the energy barrier for both the steps, and we found that the gamma attack of the sodium allyl species is an energetically favorable process, and it can lead to the formation of corresponding propargylated product. So next, what will happen when you install a hydroxyl group ortho position to the paragonal method? Whether it will form the corresponding allylated product and whether this hydroxyl group will undergo intramolecular cyclization to furnish the corresponding bromine derivative. With this thought in mind, we went on to set up the reaction, and we were happy to find the formation of the bromine derivative as we expected. Then we have investigated the scope of this reaction with the various substrate. Next. And this is the possible reaction mechanism. As I have mentioned, in the presence of potassium tertiary butyroxide, it can form the corresponding allylated product. Then the base abstract a proton from the hydroxy group, then it can form the corresponding potassium alkoxide. This undergoes the intramolecular nucleophilic addition with the allyl functionality. It can form the corresponding carbanion. The carbanion upon protonation can give the corresponding bromine derivative. So, how much time do we have? Can I continue? Okay, can I go to, can I take another 5 minutes? I can complete. Can I go to last part? Can you go? Sure. Here. So our groups also works on the use of sulfur pronucleophile. Here we would like to use our sulfur pronucleophile with a bicyclobutane intermediate or bicyclic molecules such as the bicyclobutane. Bicyclobutane is abbreviated as the BCB, which contains a 2-3 member ring fused together at the bridge carbon atom. But it is a highly strained molecule, and the strain energy is approximately 64 to 66 kilocalories per mole. And when you compare the strain energy of the smallest molecule, which is the cyclopropane, which is 27.5 kilocalories per mole, which means bicyclobutane has a strain energy of twice that of the cyclopropane. And due to the high strain energy, the central CC bond is very weak. So it readily reacts with the various nucleophiles and electrophiles and radicals, and it can give the corresponding cyclobutane derivatives via CC bond cleavage of the central bond. Here, this is the conformation of the bicyclobutane, where the CC central bond is denoted here. Though it is a sp3 hybridized bond, however, it has a high P character because of the high strain, and this bond, the central CC bond, almost behaves like a pi-like reactivity. We would like to use this central CC bond for the nucleophilic ring opening reaction with the sulfonamide. Sorry. So we have taken sulfonamide as the pronucleophile, and we have subjected this for regioselective ring opening at the less substituted end of the BCD, and we have screened various reaction conditions, and we found that the use of 20% of the serial triplet led to the corresponding sulfilamine colored cyclobutane with a very good yield with excellent anti-selectivity. After successfully developing the method, we have evaluated the scope of this method, and various sulfonamide having different substitute also underwent a vessel ring opening reaction and furnish the desired product with very high anti-selectivity. And also, with respect to bicyclobutane, also we were able to synthesize various cyclobutane derivative with very high anti-zinc selectivity. Yeah, next. Here we propose a plausible reaction mechanism. Here, the serial triplet coordinates with the carbonate group of the bicyclobutane, which further weakens the CC central bond. Then the sulfur atom of the sulfonamide regioselectively attacks the bicyclobutane. Next. Here, the sulfur lone pair attacks the less substituted end of the bicyclobutane. Then this bond moves here. Then this bond moves, and because of this bond electron movement, the one of the triplet ion is expelled. Next. Because it has used its lone pair for the nucleophilic ring opening reaction, there will be a formation of positive charge. then that will be stabilized by the nitrogen lone pair. So eventually it forms a corresponding positively charged species, which is C. Then next, the triplet ion which is formed in this step abstract a proton from this positively charged nitrogen atom. It forms a corresponding triplic acid. The triplic acid further protonates and gives the target product, and they regenerate the catalyst in the catalytic cycle. Here, we propose a plausible stereochemical model for the anti-selectivity. Here, the cerium triplex coordinates with the carbonyl group. Then your sulfonamide approaches the bicyclobutane in a pseudo-sodium position as shown here. Then one of the triplet ion abstract a acidic proton. Then it forms the corresponding unilate. This unilate is protonated by the triplet acid generated in this step in this fashion, and it gives the corresponding cyclobutane derivative in a very high anti-selectivity. So in addition to this chronic level chemistry, our groups also works on the CH functionalization. In this regard, we have published a regional selective C3 emulation of 2 piridones, and also regional selective allelic calculation of imidazopyridine, and also direct biorelation of indole using palladium catalyst. And also our groups also works on the asymmetric catalysis. We have accomplished the regioselective propagation of aminopyrrole as well as regioselective 1,6 conjugated addition of paraffin method with very high initial and tertiary selectivity. Next. So whatever the work I have presented is not possible without the sincere effort of my PhD students and master students. Whatever the work today I presented was from the Dr. Bhatima thesis, Dr. Amrita, and Kalyana Krishnan and Darshan. I would like to thank the funding agency, SCRB, STARS and CSR, including and ISAR Gnanaraj. Yeah, next. This is my group at ISAR Gnanaraj. Next. This is our campus. Most of you might have seen. This is one of the beautiful campus in India, which is situated in the foothills of Western Ghats. So next. This is the indoor stadium and hostel. Again, close view of indoor stadium, chemistry department and physics department. And this is the guest house. And this is one of the lake we have in our campus. Finally, thank you all for your kind attention. If you have any queries, I will be happy to answer. This is the saddest part, right? They don't ask any questions. It can be any silly question you can ask. I'll be happy to answer. Don't worry whether it's a good question or bad question. Okay, since we have come from the ISAR and NISAR, so in other states there are several students, whether it's a West Bengal, whether it's a Kerala, there are many students coming for research. But we are not getting many students from Tamil Nadu. So I urge you all you people to clear GATE and CSR and to apply for a PhD position in the premier institute like IIC, ISAS and IIT. Okay, thanks a lot.